Hello everybody, my lecture today is how to design a power supply for an amplifier, and of course the suitable power supply for such an application is the full wave bridge rectifier power supply. Okay, let's start. I'm not gonna waste much time in discussing how the full wave bridge operates. I believe the figures shown display exactly how such a power supply operates. I'm going to concentrate on how to calculate and how to design a power supply for such an application. Okay. Now, before we go further into the subject, let me start by explaining the meaning of the following symbols. These symbols were standard in discussing all types of previous power supplies. That was the half wave rectifier, and after that the full wave center tapped power supply, and the third now, which is the full wave bridge rectifier. Okay, let's start by the explanation of these symbols. Let me try have more focus. That will help me more. Okay, we have the IM, which is the maximum peak current. We have the VM, which is the maximum peak voltage. We have the IDC, which is the average load current. We have the VDC, which is the average load voltage. We have the VAC, which is the rated secondary voltage RMS value. This is what's written on a transformer. We have the IAC, which is also the rated secondary current in RMS value. This is also written on a transformer. We have the PT, which is transformer power. That means the VAC multiplied by AAC, and it's in volt ampere. We have the power load in watts. We have the VO in RMS, that's the effective load voltage. We have the IL in RMS, which is the effective load current. We have the IT RMS, which is the effective transformer secondary current. Like I said before, the lecture concentrates on how to design such a power supply. So it's not for the hobbyist, it's for technical people who are going to design such a power supply and to be able to select the suitable components or design for the suitable components. Okay. Now we have the VM, which is the maximum peak voltage, to equals to the root square of 2 multiplied the VAC. Actually, I'm not going to go through all these equations. I'm just give you enough time just to grasp what's written in there and concentrate in main items. We have the VDC, usually for the half sine wave, it's 0.636 of the VM. Okay, or it is the 2 over pi multiplied by the VM. We have the IAC, which equals, as we all know, 0.707. Sorry, 1.4 multiplied by the RMS, which equals the IM value, the maximum peak value for the current. And we have also the IDC, which equals 0.9 of the IAC. Okay. Now we're going to start with this power supply without including the cap to see how much power we're gonna get out of the transformer to see whether we are getting worth our money out of the transformer. Okay, so we have an example in here, and that example is for that full wave bridge rectifier without including the cap. And that transformer is always standard for all the configurations, and that would allow us to compare how much power we're gonna get out of each type of power supply. That transformer standard is to be, has an IAC of 2 amps, a VAC of 12 volts, that's of course an RMS, okay, and therefore the P total for the transformer is 24 volt amperes, and we're gonna use it in the circuit and we see how much we're gonna get out of it. So clearly the peak voltage will be 17 volts in such a case. Okay, the IM max, that's the peak current, equals 2.8 amps. The minimum resistance that we are allowed to have is 6 ohm. Okay, less than that means you are stretching your transformer and exceeding its specs. Okay, and after that we multiply the RMS voltage, the load RMS voltage, multiplied by the RMS of we multiply the RMS voltage of the load, multiplied by the current, the RMS current of the load also, and that would give us 24 watts. That means we are utilizing the transformer fully. So every watt we paid for it, we get it. If we use this power supply without a cap, okay? And as we see in here, we were able to utilize the transformer fully. That's 100% of its capacity. We got all its power into our load. Okay. Now, when we use a capacitor as an energy storage element, things change. Things are not like they used to be. See, the idea that altering the shape of the charging current or the current that are drawn from the transformer changes the RMS. Okay, so the idea, when it was a sinusoidal like this, driven into the load, we got 100% out of it. Altering the shape of that current, that short duration where you have to charge that cap, changes the RMS value of the current drawn from the transformer. That means much change in it. What's the idea behind the subject is when you are using a cap as a storage element, you have to charge that cap in a very short duration. So actually the transformer is not doing anything between the time this point up to the starting of the new point. Okay, it's not doing anything. The transformer only operates on this period only, which we call it the conduction time. And the current becomes peaky, like we see in here, and that changes the RMS of it. Of course, as many know, that peaky currents tend to have a high RMS value. Okay, let's go further into that. So in a situation like that, we have the VDC equals, as we all know, 1.4 times the VAC. You deduct out of it the ripple voltage divided by 2. This is introduced because you have that cap. So that's the middle point of it. That helps in the graph in here. Okay, that's the middle of it. That's VR over 2. VR is from the top to the bottom. VR over 2 of it. Okay. That's the VDC value, as we see in here. And down you equate the energies. So whatever energy you are getting, or whatever power you are getting out of the transformer, is delivered to the load. So this side must equal the other side. We have the VM almost can be considered to be equal to the VDC. Okay. And what we left with is the current and the time. So we compensate for the long time for the cap to supply the load with a short high pulse of current. So therefore the IP multiplied by the TC should be equal to the IDC multiplied by the whole duration T over 2. The T, by the way, it's 20 milliseconds for us here in Jordan. In the States, of course, we are operating at 60 hertz, so that means it's 16 something milliseconds. Okay, so that's the T. Now for simplicity, we equal the VM over the VDC as we said. And further analysis, that would give us the value of the IP, which is going to be peaky, like we said before. And this is how to find the RMS of any given signal. Now that's rectangular short period of current. Okay, we'll convert it to its RMS value. To convert something into its RMS value, you get the value of it, you square it, okay, then you find the area, which is multiplied by the time, the dt, okay, and you find the whole area by integrating that, and after that you average it over t over 2, because that's half of the period, and after that you root square it. So this is the rule to find the RMS for any given signal. Okay, more equations and more equations. I'm gonna slide them. You can follow whatever you want if you are interested. And I'm just gonna point the most important things to talk about. Okay, now finally we'll get to the idea. This is the very important thing that we want to reach, okay? That's the IDC max, the maximum DC current that you can get out of the transformer when you are using that full wave bridge power supply is 0.5 the IT RMS, 0.5 the IAC. So that means you get half of the current that is written on your transformer, okay? That's of course based on the conduction time. I don't know, that's probably were mentioned somewhere else in here. That's considering that the conduction time is 2.5 milliseconds, okay, or a quarter of that half peak of a sine wave. So this is the important conclusion that we reached. The IDC max is equal 0.5 of the IAC, or half of whatever is written on the transformer. The other half is gone because you altered the shape of the current. If you draw more current than this, you are exceeding the specs of the transformer, and that's going to fry it. Okay, now the same thing for other lectures previously discussed. You can get 0.35 of the IAC when you use half-wave rectifier type of power supply. You can get 0.71 of the IAC for a full-wave center-tapped power supply. This is just an information to be able to compare between the types of power supplies. Okay, now let's go further into things. Okay. Now, what's the value of the VDC? I don't know, probably I slide it fast. No, this is not fast, it's good enough. Now, to know the value of the VDC after a few equations, here's what you get. You get 0.855 of the VM. Okay. So you can get about 0.9 of the maximum peak value, that you can have it as a DC value, Of course, like we said before, with the conduction duration of 2.5 milliseconds. Okay, now let's go further a little bit. More equations. Now here's the conclusion. The conclusion that when we used a cap, we were able to get only 60% of the capacity of our transformer. That's the idea. 60%. Can't get more than that. Now, if you still remember, when the cap was not included, we got 100%. We altered the shape of the current. Now we get only 60% of our transformer. So that tells you what kind of transformer you should buy for your application based on this. And here's an example. The example that you see here for the same transformer. Okay, we saw before that when we didn't have a cap, we got 100%. Now, when we have a cap, you have all the calculations in front of you. And that tells you the value of the cap that you should be choosing to get that conduction duration of about 2.5 milliseconds, because they are all related. And it tells you how much power you are getting by the numbers, which is 60%. Okay. That's just converting the equations before and plugging numbers in these equations to get this result. Here the components ratings or values, as you see in here. I'm going to slide them, I'm not going to discuss them. Furthermore, more values. That fuse is really something. I think I'm going to make another lecture on how to calculate a fuse for a power supply. It's not something to take out of your bucket or out of nowhere. People say just put 2 times or 3 times the IRMS from the transformer and that would work, and that would be fine. To know exactly what kind of fuse you should use, this equation is exactly for the full wave bridge rectifier. And every type of power supply has its own equations, because there are a lot of reactive powers that sometimes are not considered. Okay, so things change. And here probably there's a value. Okay, so what you got in here, 175 milliamps would be suitable, T-type of course. Down there, if it was a half wave for that same transformer, it would be 250. So imagine that, 250 milliamps, that's a suitable fuse for a half wave. Or look at that, 125 milliamps for the full wave. Of course, there is an equation and there's a specific chapter for how to select these fuses. The 125 milliamps tells you exactly that that transformer was fully relaxed when it was operating. You know, I mean, the value of the fuse tells you that was fully relaxed. The same transformer, and it only needs 125 milliamps fuse. Okay, further the remarks, I'm not going to read them. You just fix that screen in there and read them if you're interested. Now this is an important thing, because this is the type of power supply that you are going to be using in a power amplifier application. This is slow just to know what is happening. Okay, this type provides a very efficient way of obtaining 2 identical outputs. That's what's written in there. Of reverse polarity, sharing a common signal. That's the idea. And how to create that reverse polarities, with equal values and to be efficient at the same time. So this is the power supply. Now what happened to all the calculations that we had before? Nothing has changed. It's all the same. What you're going to do is just the following. Now this cab is considered to be in series with this cab. So we had 1500 microfarad before. Now each one you put it as 3000 microfarad. Nothing has changed. The resistance, this is the load resistance, added to the other one must equal the other load resistance that we had before. So it's all the same, nothing has changed. Whatever load resistance we had before, we just divided into 2. Whatever the cap that we had before, we just double it and put on in series and get that beautiful center tap that you current there. By the way, no current passes this center tap. If these loads are equal, no current will pass in here. Only error current will pass that center tap wire. Error current, and that means error current is the difference between the current passing through R1 and R2 if they are not equal. Otherwise, nothing will pass through it. Just an idea. So there's instruction.